on a scale of 1 to 5, 5 being the highest, who feels like really super comfortable with middle school Common Core content standards? We're all learning. We're all learning. What about the same question, but for the standards for mathematical practice? Super confident, not still learning. Okay. Yeah, it's a period of change and growth for all of us. So let's jump in. Need to make sure that you know that the evaluation full code is here, and the sample is here because they told me I had to. So here on page 3, we talked about some of the goals for this morning, and there's the presentation description. So I hope what we talked about today fits that description that you read in the catalog. So we want to experience some Common Core mathematics problem solving in this domain of ratio proportional relationship. Probably considered to be maybe the most important one in 6th and 7th grade. We'll talk about some of these content standards and look at some of the tools your students are expected to use. Interpreting the standards is a little bit tricky, and we'll talk about some of the definition changes and some of the new expectations and some of this information that comes from the progressions documents. So when I say progressions documents, show of hands if who's familiar with. Progressions documents were written by the founders of Common Core mathematics and sort of laid out the content standards would eventually come. And I have a citation where you can go back and read them. They're pretty dense, but they provide a ton of good info. So there's, it's on the bottom of this page, as a matter of fact. It's the University of Arizona website. And so we want to talk about, as I mentioned before, coherence for the middle grades. And if we get a chance, time permitting, we will connect some of the mathematics we do in a real way to the standard mathematical practice. So does anybody have any questions before we jump in? All right. Page 4 has a list of some of the content standards that we'll probably address, depending upon time again. And you'll see that they're mostly 6 and some 7, and then a little bit of 8 at the bottom. This is really shiny. Better?
Yes.
Yeah, this is small type anyway. One thing I want to point out to you is that not all standards are certainly created equal. And it seems a little bit odd to me that some content standards just sort of kind of let you know the topic that you're supposed to address with your students. And some actually, in a very different way, prescribe the methods that you're supposed to use. And so in 6th grade, when we get down into 6RP3, they're telling us that some of the tools that we need to use are tables, tape diagrams, double number line diagrams, or equations. So they're not just telling us that kids need to do this stuff, but they're also telling us the tools they need to do this stuff. And so those are some things that I don't want to give you an opportunity to explore. Just as a reminder, when we look at the content standards, you see that the greater focus, very important word in Common Core. We're not doing everything at every grade level anymore like we were in the old California standards. We are going to concentrate mostly right here, 6th and 7th grade, and it'll connect to some of this expressions, equations, and even functions.
So there are methodologies, models that we might use in 6th grade.
Can you guys hear back? Can you?
Okay. I'll use my teaching voice.
There you go.
Since there are various models that the standards want us to use in 6th grade, which will be taken advantage of in higher grades? Are there key models from 4th and 5th grade that our students are going to be using for ratios and proportions?
That's a good question. I'm probably not the best person to answer that because my focus is mostly middle school. So I will tell you though that this domain, as you can see, doesn't come up until 6th grade.
Right.
So anybody here would know of, I mean, certainly the double number line. Number lines are a huge focus from the start. So I mean, that's something I can speak to.
I know in elementary, the introduction to fractions is pretty first because they are starting to use the number line, use the heavy emphasis that students have developing responsibility around what it is, and how you're going to strategically partition, which then leads to the double number lines, which then leads to the tape diagram. With the tape diagram, start with that. Because they start right from the ground.
Right. I'm just hoping that the students have a common experience with defining the unit in a flexible way, that this would be something we could all build on.
That is the key. That is the key. And in this time of transition, because we not have all of our kids are not being not have gone through that journey yet. It's going to be something that we want to put in somehow scratch.
Certainly proportional reasoning happens at a very young age. I mean, when kids sort of start learning the relationship between addition, as for repeated addition is multiplication, this idea of fractions. So, proportionality comes up in a less formal way. Sure. The inverse relationship between multiplication and addition. There are lots of so hopefully with this idea of focus and we're supposed to have fewer topics per grade level and dig deeper, it's going to be helpful. The coherence I think will be very visible when we're doing our 6th, 7th, and 8th grade, just snippets of activities. And then certainly this idea of rigor in the Common Core sense that we have equal parts conceptual understanding, procedural skill, and problem solving application. Whereas in the past we were doing almost all procedural skill. It seemed to be. So a couple of quick notes before we start your activity. One of the things that stood out to me in the definition of ratio and the literature about it was that we're talking about sort of an ordered pair of numbers, the ratio of A to B. We have very similar notation, columns. There's a lot of language. A for B, A for M for G. What we don't see is the use of fraction notation with ratio. In other words, A over B, A keeps A divided by B. That's not considered ratio notation. So you shouldn't see that. If you, whatever 6th grade curriculum materials you're using, if they're using fraction notation for a ratio, they miss something. There's you infer from what we. That's our unit rate. So when we made that 3:2 ratio a fraction, they call it in Common Core the value of the ratio. So a ratio is two numbers, 3 to 2. The fraction 3/2 is a number, a singular number, 3/2 divided by 2. That's the unit rate. So that's what we understand when we read the fractions documents. Any questions about that? I've talked about this with teachers a lot. And some people, it's new and it feels weird. It's not what we're used to. Not how we learn it. It's not how we teach it. The kids don't know the difference. This isn't going to be a big conversation you're having with kids. You're not supposed to introduce it as a fraction. When we look at the fraction, it's a number. Fraction, then that number is the value of the ratio, which is the unit rate. 3/2 or 1.5. So I just wanted to get that out to start. Any questions before we move on? Yes?
It's kind of hard to hear if you're competing with the air conditioning.
Okay.
We're not really getting
Okay.
full impact.
Okay. I'll try to speak up. Is that better? Thank you for letting me know. So you have a series of cards at your table. I'm happy to I have plenty more, but the idea is that you're going to have some discussion in pairs or more. If you want another set, I'm happy to give you more. So consider this situation. You're going to make a equation, and you can use a combination of water and grape juice concentrate. You know, or for 3 or however you want to use a structure that is draws a little bit differently. So these cards, parts, the dark ones, parts of the grape concentrate. The light ones are parts of water. And so your job right now is to discuss these 4 cards and sort of order them in the greatest to least gravy, or vice versa, least gravy and most gravy. And so which will taste the most gravy, what's going to taste the least so. Questions? Okay, have that discussion.
6th grade, it's in there. It's the orange mixing. I tried it, it's really good. So, didn't miss the movement.
So those are 4 grape juice mixed
Yeah.
with grape concentrated water. What combinations are going to be least gravy?
Oh,
Most
okay. Exactly what I mean. For example, the ratio of orange to non-orange is 2:1, right? But how much of the thing is orange is 2 thirds. I think green seeds. And then I had them write a ratio on one side and then the fraction of the change on the other side. And they started saying that they're not the same as how are they different.
Gotcha.
It's great, especially for these are the fractions of the change. That's how much of the change is orange. These are the ratios.
Right.
And there's good editing. This one is easier to see this one. C and J. What I did, I wrote the fractions and I just compared them. I knew this is more than 2 is 0.66. This is 0.33. 374. This one is less than that. That's 5. It says you should U and C. There's the same.
All right, folks, we're going to move on and have a little bit of discussion. A lot of people are done, some people are still kind of finishing out their discussion. So let me try to get y'all back together. Let's try to have a little bit of discussion about, first of all, what the correct order from, let's say, from least to greatest is, and have some examples of ways you might not about thinking this through. And then we'll go ahead and talk about it below. First of all, which is the least? A. Then and then B. So I don't have to ask about the last one. So what are some strategies that you use? Let me ask you this. Did anybody just naturally go to fractions?
Yes.
and let's back up a little bit. If you gave this to your students, and without a whole lot of instruction and background, would it be intuitive enough for them to dive into and have these discussions about what would be more grade B and less grade B?
I actually did this in my class.
So you did this in your class, this exact thing? Or
It's all, yeah, it's not grape juice, it's called orange mixture.
Okay,
And it's on, should I say it?
go ahead.
It's on Mars, it's the assessment project website.
So it's a Mars test.
Yes,
Yeah.
it is.
Yeah, I mean this is a very common
Yeah.
kind of idea out there.
And
Even before Common Core.
but the kids got a lot out of it. I mean, the way they set up over there is that they see that there's a difference between ratio and fractional part of, the drink being an orange or grape or whatever. They truly saw that, and they figured out that the fraction is part of a whole, but then the ratio is part of one to the other, and it part to part, yeah.
So what you're saying is it was accessible to your students?
Yes.
And they were using fractions?
And not in the beginning, no. They were looking at no. Okay, which one? No, they weren't. But when we finished, they got it.
Okay.
True.
And
Yeah.
I'm not advocating yes or no for fractions.
Right, I know.
I just had a feeling it might be natural for adult or kid. It might be natural for fractions.
I think having these statements for the students to discuss is very important in terms of getting them started. That is, in some ways, you almost want to reward them for which of these concepts, can you disprove and how? Because, the tendency is to wait for the smartest kid in class to decide what the answer is. They're not putting effort into the grid. But my approach is, it's not the first step of the students, is to always look at what is the total number of parts. And in this case, since I wanted them to stay with proportions, I used multipliers on each of the ratios. So the ratio on A is not 2 to 4, it's 2 to 6. And then you use the multiplier in front of that to get everything up with the same number of pieces.
So it's a part to whole.
So it's a part to whole. But that's for my introducing myself into the discussion after they've had a chance to get engaged.
Yeah, I sort of have this philosophy with students that if you can dole out the least amount of information possible, it's better to help them kind of create their own meaning. Because we see when kids get stuck, we can always pull them back and start having some conversation. But I hate giving them too much information up front and kind of stealing that process from them of problem solving and creating that important understanding.
Yes. My kids did not go to fractions in the beginning.
Yeah.
They actually look at the proportions and how much they did not.
If you don't say anything about it, who knows what they're going to do? It's a great way to really assess thinking in a very formative way.
Not friend of mine, working Christian. Very much. I probably would have used it in terms of likes and dislikes, social media, Call of Duty, field. You see what they're interested in. I mean, Rachel's great, all that's cool. You get a piece like that, they're probably going to be serious far quicker.
Make it your own. Make it your own. Absolutely. If this inspires you to come up with something cool, go for it. Go for it. Absolutely. Again, this is a classic kind of thing that we see is in terms of food kind of products and mixtures. It's just a very common context for ratio.
Mm-hmm.
And it's intuitive. Other things. Right. Yeah.
One of the things I wanted to ask was, how would you, if you find that one person or two people are talking about decimals or they're talking about fractions, and this is turning off the rest of the students in the group because they feel inadequate, what would you say to that group to get them back to proportionality?
We're pretty much mid-unit right now, and where my students are is they're manipulating the pictures so that way they create equal amounts. So what my students would most likely do is draw this picture again until they get 63, a mixture of 63, and then they can see and compare the amount of rate that's in each. So they're relying heavily on visual right now. I think if you push the visual, then that may bring some other students along that maybe aren't comfortable with the decimal rule.
And by the way, thank you for saying that because you're reminding me of something that's very important. When I pointed out that standard and underlined all those tools, many of them are very visual. And that's one of the common core goals of these standards is let's not jump right to fraction notation. Let's not the word proportion, as an equation doesn't even come up. Certainly not in sixth grade. I think there's this idea don't teach kids in sixth grade to set up proportions and cross multiply. Maybe in seventh grade, but the whole idea of it being very visual and using pictures, diagrams, and organizing numbers and tests. So that's important. And this is intuitive. I'm not sure about the discussion of, well, if they're using decimals and fractions, how do I push them this way? I think if you're just making sense of it and using fractions, great. If you're making sense of it in other ways, great. What are some other ways that some other discussions that you've had or you've heard at your table about breaking this and non-breaking this?
No, I love just the alternative process of it.
Okay, I mean, how do we know? How do we know A is the least grade from? And let's refrain from fraction. But let's just look at like pictorially. Like how would we make sense of A being less graded than the rest of those things? Which one makes sense?
I would look at maybe the color cups and see that there's more like color cups on E than there is an A. Trying to stay away from fractions.
But if there's more water in E, does that make it less graded?
No, because then I would look at the dark colored cups and have to do determination. And I could do also maybe a 1-to-1 match
So keep going with that thought. Keep going with that.
Yeah.
I think about that.
Okay. Jump in.
I would actually have to maybe circle circle one with one and see if there's another one that what is left, and then you can add it on. I would actually, yeah, like the unit, but yeah, and then see, you know, you have two more white ones that you can add to each group, so it'll be 1 to 2. I mean, yeah.
So you say compare to like 1 with 1, 1 with 1, 1 with
I would start with that and then say, okay, what's left? So how can we divide that into 4 groups, the extra one?
And I kind of, this way of question, but I kind of want, rather than being telling, you know, what we getting from, what kind of things we're getting from the students. And that's those statements at the bottom of the page are there to promote a discussion about, you know, obviously most of those, I believe, are incorrect. Thank you. How many of them are actually correct? One, maybe one. Yeah. You know, we want to get those, having the error analysis going on is super important. You know, let's confront those things that we think about incorrectly and discuss whether they're correct, because they're common, incorrect thoughts. Any other thoughts about how you think about
You were suggesting that you compare one grade to whatever the national quantity of non-grade is. I thought of it as matching 2 grades to the quantity. But actually, I think what you really want to do is to show the class that you can be reductionist to a standard quantity, or you can increase it to a standard quantity. So, you know, part of the thing with this, if you want the totals to be common here, you've got to go up to 126. Well, most of the students aren't going to have enough patience with it, either to draw it or to even count it out. So we probably don't want to go all the way up to total equality, but we just want to go to a usable ratio based on a standard quantity.
Well, and with that thought, I'll give you a little hint. If you increase all of those proportionally, so you have a 12-part grade, you can come up with nice whole numbers of water. It's in all of the 12 grades. You just look at what's going to add more or less water. So those numbers all they can be pretty friendly. You can certainly, if you understood unit rate per 1 grade, how much water, whether it's full or dry. So there's just 2 ways to do it. Let's talk about a couple of these. Number 2, our kid's going to do that. They're going to think that way. What that's in that grade is in that greatness. I don't see it as a big problem. Problem 3 there. I see that as being a big problem. What's going on with 3?
I think it's a vocabulary thing where it says the crazy thing. They're making the assumption because there's one that's on the path that it's going to be.
So if I have something, and if I have any of these cards, any of these mixtures, and I add 1 grape and 1 water, will it taste the same?
Those 2 are very close together. That's why
Let me be more specific. If I look at these 2 cards and I add 1 more grape and 1 more water, will C still taste like C? Or will I have changed C? Let's see. I added 1 grape and 1 water. the C case the same, or I change?
Change
the portion?
But they won't,
Because it's what actually, yeah, that's right. You said C, we're not saying, okay? So it's obviously changed, so.
So the difference is that, if you have a half relation, it's gonna taste the same no matter what volume. But if you have half, in a cup versus half in a gallon jug, and you put 1 cup of water into the cup, and 1 cup of water into the gallon, then it's really clear which one's.
So that's using an example of the extreme example.
just kind of number 6.
Extreme, like when kids are confused with fractions when 2/3 and 3/4. Well, they're both a unit fraction with whole. You might get confused which is bigger. Like if you have 2/3 and 99/100, they're both still a unit fraction with whole. That seems more clear than 99/100. Really good technique. I'd like to push this question because I don't know what you're thinking, but it's this idea of proportionality where additive reasoning like this doesn't work. That equivalent ratio idea where we're multiplying by the same factor. That's going to get us to the equivalent ratio. If we add the same thing, it's not. I think there's some confusion with kids about that.
The students that this example is important are those students that are still multiplying using their fingers, and the ones that have fully learned their times tables, because they haven't fully made this jump from addition to multiplication and seeing that those are very fundamentally different things. They see the connection, they don't see that they're different natures.
So I want to point you to the back of the packet. Some of you have already looked at this. If you wanted to use this in the classroom, those are 8 cards that I made up. I'm going to do it before. I've had some discussion with teachers, and they thought, let's do this with 4 cards, the picture ones, discussion, and then introduce the other 4, where you have some language there, some words, some different notations, a fractional relationship in part F, and then a table in part H. And then you use some those and say, well, where do those fit in these symbols or in this and that is pretty challenging. You have some stuff there. So I want to take the time for us to do it now and move on. And you can probably create these if you wanted to. If you wanted to just have fun with it, you can give students all 8. You can do that too. So the next thing, so we were talking about tape diagrams. A nice visual, and you know, it's something you can prescribe. We can make sure everybody's understand these. I'm sure, and I don't see a lot of more math questions. I'm sure that your kids in 6th grade for sure, maybe 7th grade, encounters tape diagrams as well as other number line diagrams. It's not the only reason to use it, but it's a very nice visual tool. We see them in 2 different ways. Here's a grade to water ratio of 2 to 4, and some people prefer the 2 to 4 tape diagram on the left. Some prefer the one on the right. I don't care. It's easier to draw. As a side note, the first time I saw these, Singapore map, got redeveloped anybody? So I don't know if they decided to include these in the Common Core standards because Singapore is one of those top nations in mathematics. So I suspect that might be what the NPRC diagrams. So a challenge for you. Draw, looking on maybe the back of this handout, draw a tape diagram for card D and card F. Because I think maybe some of you never used tape diagrams. So draw a bunch of tape diagrams for card D and card F. Go to the back. sure with all the partners and make sure we get it right.
I think that's. You got the same thing. That was good.
Okay, ladies and gentlemen, let's come back together again. It's a discussion on frowns. So thank you. With card D, what's the twist with card D? Okay, parts of whole. So there's how many waters to how many grape? So two to one, which makes a total of 3. Okay. So the fraction in card F is a little strange, and people were kind of, there were some ideas and some discussion and some frowns. And Vanessa was explaining to her partner, or a couple of partners, and they're like, "Oh, that's cool." So she agreed to come up and show us, so.
Oh, yes, I agree.
She agreed. So let's take a look.
I'm allergic to chocolate, so that was one.
I want to hear it.
I said for every water, just for every, I'm reading what is there, and I'm drawing the picture. There's 2/3 cups of grapes, or grapes, grape juice. And I kept on going until I was able to fill up my grapes. So another cup of water for the 2/3 of grapes. Another cup for the 2/3 of grapes. And then I got here and I said, well, I can take these two and bring this one here and this one here. Two grapes to 3 waters. I don't know if I just explained that clearly, but
Everybody's best strategy. You get the feeling that you're supposed to use whole rectangles. You don't take that. So anyway, that's one of the problems. Several ways that we do it, but I like that flexibility of thinking. That I mean, it's something that kids learn when they're young. This idea of proportional increase within fractions. So it might not be the first time kids do something like this. So let's look at 2 and 3. Some of you may have gone on and looked at it. So kids are confronted with problems and they're expected to use the tape diagram. And so here, when Alex has to make 12 gallons, he notices that he can just take his 6, rectangles and double them to get 12 rectangles. What's going on with what Andrea wanted to do? You may have that discussion yet? No. Have that discussion, because I don't want to use Alex's method if I'm. So talk about how that tape diagram might work in a more efficient way. Unless you're doing it wrong, we have a whole bunch more days.
Which stage?
Yes. Okay, guys, let's come back together again. I'm seeing something that's pretty common, so I don't want to talk over you. I'm sorry for still having some discussion, but a lot of people want to move on.
underneath.
So what's going on here where we don't want to draw a whole bunch of tapes? What's a more efficient way that you would want to lead your students to somehow? By giving them this kind of problem, you're pushing them to not want to do a lot of drawing. What might they do organically, hopefully, rather than you having to tell them what could happen here? And it would be easier to show it, or do you want to?
Yes.
It's up to you.
Okay, so I thought of this as looking at the whole amount, so 6. And we know that Andrea needs 108. So I was thinking this from 7th grade as scaling up. So you would times that 6 by 18 to get to the 108, so that would be your total. So then you see here that there's 2 grade. So then you would do 2 times 18. And then you would take the 4 waters and times that by 18, and that would give you the 36 and the 72. So I thought of that as scaling up.
So what does each rectangle represent in that case?
18,
We did something very similar. So and thank you very much. So that multiplicative reasoning is really important. All right, let's move on to the double number line diagrams and tables. By the way, when we look back at the tape diagram, the progressions document suggests that tape diagrams are good when the units are the same. So in this example, we had parts of grade, parts of water, cups to cups, ounces to ounces, gallons to gallons. Same basic. Here we are with the double number line diagram, and those same progressions documents suggest that double number lines are good when units are different, miles per hour. So here's some information about Alberto jogging. Fill in a table, and then the tape diagram below it. We may not do any more than the top. If you want to go on to the bottom again. I want to focus on these. Yeah. Okay, let me bring you guys back together again. Let's look at that top table first. What kind of thinking and in what order might you fill in that table? Right? Anybody fill in that table? Does anybody want to share? They're like where do you go to first in that table? Okay, which is, and then what?
And then I find
Somebody who went right to here?
yeah.
Okay, multiplying both by 2. Can anybody keep going straight across? That? And what now? Okay. So where now? So that's interesting. So nobody went, oh, that's times 1.5. Okay. So who started at 2? Times 30? Okay. Did anybody start in a different place? So I heard of unit rate. You went to the unit rate. When did you start with unit rate? Immediately? Okay, well let's go to this one. Where did you get this column? From the first one?
Yeah, divide by 2.
Okay, I heard taking half, divide by 2. You know the funny thing? Your 6th graders know that dividing by 2 is the same as finding half? Iffy?
No.
Okay. Whether we use fraction or decimal there. What about doing this one?
I divided by 5.
Divide the first thing by 5?
Yeah.
Anybody do something different? Anybody divide this by 10? Okay. What is this? Is that it? And then here, where does 2 come from? Okay. And you may use fractions, decimals, whatever. So something that's interesting to me is I've had some teachers tell me that a table has to be in order, like least to greatest, and this bothers me. I hope this doesn't bother you. You might skip around, depending on the given numbers. Somebody might skip to the middle of the table and then come back to the left. It's sort of up to you how you want to do that. Now, with the double number line, we don't have that luxury of skipping around in the same way. You can skip around, but it's got to be scaled. Over here, they were talking about, my kids have a hard time scaling number lines or axes or graphs, and I'm sure you've all experienced that.
Yes.
That's just something we have to confront and work with and help our students. And we were saying that, scaling number lines is going to happen pretty early on the board because kids are using them in elementary school. So I hope in middle school they've got more experience now with number lines and scaling. Kind of curious now, that first tick mark, what, I want to know what you decided to put there. Did anybody put the 5 and the 2
No,
on the first?
I put 1.
Okay. Who put the unit rate in 2.5 and 1? With any other different ones? Those the only 2 things?
I didn't want to do this. I didn't want to talk to this. So, yard per second.
Oh, you did the 1 and the 4/10, the 2/5. Okay. Maybe do anything different?
I did the 5 and the 2 first, and then between the 0 and the 2, I took the 1.
Okay.
And that's how I got my grade.
So that's nice too, knowing that just because those like tick marks are given, you can still go. So that's an interesting thing to see how people do that differently. Let me just for kids here, just kind of accentuate the different unit thing. If I was comparing cups of grape juice and cups of water here, and I see 5 cups of grape juice and 2 cups of water in the same location, it would be weird, I think, to see 5 cups and 2 cups in the same relative place. When I see 5 yards for every 2 seconds in the same place, I would never confuse that. Yards and seconds are very different things. So that's what I infer from reading that line. These are different. Take diagram on that for some. That being said, I've had teachers say, my kids use double number lines for the grape and water, and they're not confused. So, this is an example there of measurement changes. You can use double number lines for changing units of measurement. That's in one of the standards. I don't want to move on though. Some of you may have flipped to page 10. I wanted to give you some more double number line applications. 6th grade. Oh, this is interesting. Okay, so 6th grade standard says that kids need to find percents of numbers. They also need to find the missing value, not just the percent of something, but the missing whole. But it doesn't say the missing percent. That's not part of the standard. In any case, double number lines are a great tool for dealing with percent. Side note, the standard talks again mostly about how many percent of a number. There is no standard that I've been able to find that says kids need to know percent as a number. In other words, 1/2, 0.5, 50% are equivalent. So when I say 1/2 is 50%, I'm talking about 50% as a number, as a count. There's no standard that I've seen that you have to do that. So just be aware of that, because that's obviously something necessary for you to be able to do when you're finding that percent up. One of the ways that the kids are supposed to do it is, like, if they're finding 30% of 50, they need to know that they can multiply 30 hundredths times 50. But I think it's a nice visual to work up to that procedural way, doing something like this. Has anybody ever done percent on a double number line? A few of you? Okay, so let me set the stage. So here, when it says, what percent of 80 is 32? Here's our whole 100% at top. So here's our whole 80. I'll tell you right now, these are 10 parts. So what is each of these 10 parts worth? I heard 8. In other words, we can count by eights, 8, 16, 24, etc. And then over here, of course, 10%, 20%, and so on. Fill in the double number lines and figure out what goes into the blanks at the top. Is there any questions? What are you going to try? Share with partner. Usually explore combinations.
This is a good one. I love this. Very good. Very good. I love it. I love this. Seriously. Oh, my kids can drink this, but this is really good. I never even thought about it.
You guys good?
This is great.
You like that?
Yeah.
It's kind of neat.
I love it.
I like it.
Yeah.
Okay, so let's come back together again. I'm getting a lot of positive feedback on this number on 2%.
Yes.
So I hope you like it. It's a nice visual. Again, sixth grade, just a reminder, sixth grade, we're not setting up portions. But in seventh grade, maybe you do. And I want you to take a look at this slide over here.
Yes, please.
So here, Joanne, 35 cents, 7 copies. So there's a ratio. You can make a double number line out of it. So you can kind of see 7, 35 cents. The next one, you can count on the double number line. But think of this as a transition to setting up proportions. You know, when we teach kids to set up proportions rules, like be careful of the units. You know, if it's money and number of copies, we're like write money here and write number of copies. Like it's that the guide words. And make sure to put your thing here and your thing here and put the same thing here. And the double number line is really neat because you can see if I'm looking for an unknown, the X or the Y, I can see the 7 over 35 cents and the 21 over X. And all I have to do is sort of write those in proportion form, the equal sign. Got a simple proportion that pops right out of the double number line diagram. Same thing for a table. If those numbers were in a table, you could do the same thing. But the horizontal alignment lends itself very nicely to setting up proportions.
Is there a reason for converting the 100 into the proportion formula?
I'm not sure you guys are hearing the question. Can you?
Okay, I noticed that on the top you have the 100 on the bottom in the proportion.
Yeah.
But on the bottom, when you look at the number line, the 100's on top. Is there some reason why we have to convert?
No, and that's a good question. And the interesting thing is, for 4 cents and 25. They're pretty good with that. And so I'd do that, and then the 100 would have to be at the top, because everybody would say, well, that's full at the top. You know, so if I had it the other way around, people would complain about that. But in terms, I know what you're saying. So I'm setting up a proportion, and it's blank over 100. It'd be nice if the 100 was at the bottom of the, yeah. So if you were going to use this, it's up to you. If you want arrows up, 100 at the top, arrow down, 100 at the bottom, totally your call. Just like that, arrows to the right. I wouldn't have a double number line with arrows to the left, though. See, that's another thing. That's another reason, actually, that we did this. Because they're number lines, and with these ratios, we're not dealing with negative values here. So the number line going up, 0 at the bottom, you're on the axis. You're going to want 0 at the bottom. Same, and then 0 at the left, and then you go to the right because everything's positive. So it wouldn't make sense to have negative percents and negative money and negative numbers up. So that's another reason.
I guess bottom way should be up. That makes total sense. Everyone can convert.
Of course you can. Of course you can. 100 over blank and 80 over 32? Absolutely. Absolutely. Okay, next. Again, we moved into 7th grade. In 7th grade, they make a big deal out of testing for a proportional relationship. So I want you to look at the tables. I've graphed the points for you. And think about those questions, the checkpoints below each grid, and see if those are yes or no questions, and if you can fill in information there. Testing for what we call a proportional relationship. Yes.
familiar numbers along a straight line, sometimes you converge with
The last one was very interesting. So all of these have the same ratio, but then the kids get real 4.5 grade, and it's like stops them. And then they got actually, and I figured it out by cross multiply and taking the money. This is interesting. It's, yeah, the ratio is 3 to 2. But this one, 4.5 to 3, it throws them off. It threw me off as a teacher. Okay, I gotta figure this out. Yeah, I gotta figure this one out. So this is definitely the proportional. And this one, I'm guessing. Okay, you know, this is what I teach you in my 6th graders, because when you get to algebra, because I've taught algebra before, and the graph can be continuous or discrete. Discrete is you have the points, you can enter in it. If you join them, when you draw a line, what does that mean? That means every point on that line is applicable, right? But for example, here, the relationship is between what? Number of tables. You can't have half a table, right? So that cannot be continuous. That's what I looked at. The number of bags of feathers for pillows. I mean, I cannot have half a pillow or I said I wrote this grade for both of them, but that's what the difference is. And that's big in algebra class. And the sooner we mention it, when they get there, they kind of get it. My kids have no clue. So I love teaching it starting, and I went to actually and they showed us how to actually graph with calculators and stuff. And then because you teach sequences,
I don't think most people have done this, but I wanted to have some discussion. It took a while to get into the world of 7th grade. Some of the 6th grade teachers are unhappy now because it's the 7th grade stuff. So I want you to see where this is going in 7th grade. First of all, looking at these relationships to see if they're linear is important. That feeds into 8th grade big time.
Yes.
Linear function is like the big idea in 8th grade. We're almost encroaching on 8th grade territory. In 7th grade work. Continuous or discrete, I just think is a fun discussion. We were discussing at the back table about whether bags of pillows can be fractional amounts. Probably not. It's probably discrete, separate data, but we could maybe conceive of it differently. Certainly, something like time is the most sensible continuous. Money could be, except for in 2 decimals. Yeah, in practical sense, what's 0.00001%?
That's true.
Now, here's the big question: what constitutes a proportional relationship here? Which of these is? Which of these isn't? Why? What does it look like? So, why is the first one a proportional relationship and the second one? Because
the ratios are the same. The ratio of x to y is the same.
So we can look at a couple of things. We can think of multipliers. Is there something that we're doing to the 9 and the 6 that we can get 18 to 12, and 3 and 2, and so on and so forth? I mean, can we multiply or divide any of those numbers by the same thing against something else? Because certainly we can't in number 2. If I double one table to get 2, and I double $20, it's not going to be 25. Right. So that's one tip off right there, that it's not proportional. A proportional relationship on the graph is always going to be a line that goes to the origin.
Yes.
So in that second problem, there's some sort of cost up front. You're having to pay kind of extra in a sense. It's still a constant increase of $5 per table. But you're not starting with 1 and $5. There's like an extra $15 in there. You can have a discussion about interest. What does that interest mean? So 0, 0 is on the first line. Remember definition of ratio. The ordered pair has to be they both have to be greater than or equal to 0. Only one though can be 0. So a ratio of 0 to 0 is actually not by definition a ratio at all. You could have, like at this table, there's a ratio of 7 women to 0 men, and you can have that as a ratio. There's no value in that region because the fraction 7 over 0 is not defined. Teacher knowledge. Well, you don't have to worry about that too much with your kids. And here's one thing I really do want you to see.
Yes.
This point 1, what's the point here? 1 blank. What does that 2/3 represent in the context of this problem? 1 2/3. What does that 2/3 represent?
That means for every bag. Oh,
Keep going. For every bag,
there's 2/3. I mean, every bag fills up 2/3 of a pillow.
what you're talking about is the unit rate.
And that's the slope.
Yes. You hear that? That is the
Slope.
So that's the connection we're making in 7th and 8th grade. In this relationship here, the point 1 blank is the unit rate. It's how much of that per 1 unit of the other, and it is the slope of the line. We could write the equation y equals x. B is 0. It's at 0, 0. So for those of you in 8th grade, that's kind of where it's leading. So even though 8th grade doesn't have any ratio proportional relationship stuff, that's one of the big payoffs, and then your function is so important. So I want to I want to finish up here. I'm not going to keep going. I just want to point out there is a last page that I threw in here that is pretty interesting. It's 8th grade. It's totally 8th grade. There's a standard that connects ratio and proportional relationships to expressions and equations, to linear functions, to transformational geometry, which is a big deal in 8th grade. And you're looking at the slope of a line, you always use these triangle pictures, and you show, part of the standard, you show that these triangles are similar. Similarity is a big idea. Congruence and similarity is great. So you actually prove that those are similar triangles, and they have, and then there's the same ratio of rise to 1, if you will, and it is the slope of the line, and there's all kinds of stuff that connects in a very nice coherent way up through 6, 7, 8 grade. I'm sorry for rushing through this last part. If you want to stay and talk, I will stay. I'm also at a booth in the exhibit hall, booth 427. 427. If you want to come visit at 427 and talk about math and look at lessons and stuff, I'll be over there.
Thank
Yeah, please remember to do the evaluation. And I can collect cards if you want me to. If you have them, if you have them, collect cards. Thank you.